Hello and welcome to your ultimate guide for the D487 OA, Secure Software Design course. My goal today is simple: give you everything you need to fully understand the key concepts, master them, and walk into your D487 OA exam with total confidence. In this video, we'll cover information security, threat modeling, secure development, security testing, maturity models. With over 100 plus success stories, we have proven our videos will help you pass your exam on the first attempt. And remember, our website offers free exam guides and practice questions to help you ace your D487 OA exam. You'll find the link in the description below, so be sure to check it out and get the resources you need to study smarter, not harder. So let's get started. So here is where we start. Software is behind every system that matters. Banking, healthcare, transportation, defense, energy, all of it runs on code. When that code has security flaws, the consequences go way beyond inconvenience. We are talking about data breaches, financial losses, regulatory penalties, and in some cases, real physical danger. That is why software security is not optional. Now, here is the part most students miss on the exam. There is a real difference between software security and application security. They sound similar, and people swap them around in conversation, but the textbook draws a hard line. Software security means building security into the code during development. Application security means protecting the software and systems after the code has shipped. Think of it this way: software security is like building a house with reinforced walls, proper locks, and a solid foundation. Application security is putting a security guard outside a house that was already built. Both matter, but if the house itself is weak, no guard fixes the structural problem. The exam will test whether you can separate these two ideas clearly. The reason the industry cares about this distinction is money. Fixing a security flaw during requirements costs almost nothing compared to fixing it after release. BIRM's research found that defects discovered in the field cost 50 to 200 times more to fix than ones caught early. Other research puts the ratio at 100 to 1. Find problems early or pay later. And here is what makes this even worse in cloud and SaaS environments. When you have multiple versions of an application running in the cloud, a vulnerability in one version can expose all of them unless you have strong network segmentation in place. Even then, a sophisticated attacker might get through. Patching after the fact becomes a nightmare when your software is everywhere at once. What we just covered is exactly the type of material you will find in the free practice question bank I mentioned. These are not surface-level questions either. They test whether you actually understand why early remediation matters and how cost escalates through the life cycle. Go grab those questions from the link below when you are ready. Now let us talk about the 3 security goals that the industry considers non-negotiable for any SDL. These are confidentiality, integrity, and availability, collectively called the CIA triad. If your exam asks about the 3 most important SDL security goals, this is your answer every time. Not reliability, not portability, not efficiency. Confidentiality, integrity, and availability. Confidentiality means keeping unauthorized users, whether human or software, away from information they should not see. Authorization checks whether someone has the right role and privilege. Authentication confirms they are who they claim to be. Both properties work together to enforce confidentiality, and you will see exam questions that test whether you know the difference between those two. Integrity is about protecting data from unauthorized modification or destruction. The data has to stay accurate and reliable from the point it enters the system all the way through storage and retrieval. Encryption, digital signatures, and public key infrastructure are examples of how you maintain integrity. If someone tampers with data in transit and no one catches it, integrity is gone. Availability refers to the percentage of time a system is operational during its normal hours, excluding planned maintenance. If your software goes down because of a denial of service attack or a poorly handled crash, availability has failed. The exam will sometimes try to trick you by including terms like reliability or portability alongside CIA options. Do not fall for it. Here is a quick way to lock CIA into your memory. Think about your bank account. Confidentiality means nobody else can see your balance. Integrity means the bank cannot randomly change your balance without a legitimate transaction. Availability means you can log in and check that balance whenever you need to. Every security decision in software development traces back to protecting one or more of these three. Quality and security are related but not identical. Secure code is not automatically quality code, and quality code is not automatically secure. Quality is measured by ease of use, reusability, and maintainability. Security is measured by whether unauthorized users can access assets they should not touch. You need both, and the development process should be built on principles of each. Here's the catch that the textbook hammers on. A developer can write beautiful, efficient, reusable code that still lets an unauthorized user walk through the front door. Unlike quality, which can be somewhat subjective, security is binary in the worst way. Sensitive information is either exposed or it is not. You do not get a second chance to fix that after a breach. The exam sometimes asks about the relationship between quality and security programs. The textbook says they should at minimum collaborate closely during development. Ideally, they should sit in the same organization under the software development engineering department. If you see an answer about keeping quality and security teams completely separate, that is wrong. I know we are covering a lot of detailed information, and you might be wondering how to practice applying all these concepts. That is exactly why I put together those free practice questions I mentioned earlier. They will help you work through problems that combine CIA with real-world scenarios, which is exactly how the exam frames its questions. Now let us move into threat modeling and attack surface validation, which the textbook calls the most time-consuming, misunderstood, and difficult parts of the SDL. This is the work that requires a seasoned software security architect, someone who can think like an attacker and imagine every path an adversary might take to exploit the software. The idea behind threat modeling is straightforward, even if the execution is hard. You're trying to answer three questions. What could go wrong? How bad would it be? How can we fix it? When done correctly, this process happens early in the project lifecycle, before code gets written. Finding design flaws at this stage saves enormous amounts of time and money compared to finding them after deployment. Threats to software can be categorized by intentionality. A threat might be unintentional, like a misconfiguration. It might be intentional but not malicious, like a well-meaning employee who bypasses a control for convenience. Or it might be outright malicious, which is what we typically mean when we talk about attacks. Only malicious threats result in actual attacks, but all three categories can compromise security. The attack surface is the set of entry points and exit points in an application that an attacker could reach. Code restricted to local access by an administrator has a smaller attack surface than code exposed to remote access by anonymous users. The more accessible your code is, the larger your attack surface gets. Testing should cover every code path that falls within the attack surface. On the exam, you will likely see a question about when threat modeling is most effective. The answer is before code development and commitment, not during integration testing, not post-release. The earlier you identify security risks and manage them in the software lifecycle, the better your outcomes. That principle shows up repeatedly throughout this material and on the exam. If some of these more advanced concepts around threat modeling feel challenging right now, do not worry at all. That's completely normal, and it is exactly why I created that practice question bank. Working through scenario-based questions about threat categories and attack surfaces will make this much more concrete for you. Now we need to talk about the SDL itself and how it maps to the standard SDLC. The Security Development Lifecycle is not the same thing as the Software Development Lifecycle, even though the acronyms are easy to confuse. The SDL is a set of security-focused activities and best practices layered onto whatever SDLC your organization uses, whether that is waterfall, agile, scrum, lean, or a hybrid. The SDL has two primary goals. First, reduce the number of security vulnerabilities and privacy problems. Second, reduce the severity of whatever vulnerabilities remain. Notice it does not say eliminate all threats. That is a trap answer on the exam. The goal is reduction and management of risk, not elimination, because total elimination is unrealistic in any real development environment. The most well-known SDL model is Microsoft's trustworthy computing SDL, which has been evolving for over a decade. Other popular models include the BSIM SDL touchpoints, the OWASP Code Review Guide, and Cisco's Secure Development Lifecycle. Each takes a slightly different approach, but they all share the same core idea of integrating security into every phase of development. The authors present their own SDL model with 6 phases that map to typical SDLC phases. Phase A1 is security assessment, mapping to concept. Phase A2 is architecture, mapping to planning. Phases A3 and A4 cover design and development. Phase A5 is ship, mapping to release and launch. Post-release support activities map to the support and sustain phase. What makes this model different from some others is that it includes post-release support activities. Most small and mid-sized companies do not have a dedicated product security incident response team. So the SDL has to account for things like external vulnerability disclosure response, third-party reviews, post-release certifications, and security assessments for new product combinations or cloud deployments. Remember that mastering these concepts takes practice and application. The free practice questions I built are designed specifically to help you take what you are learning here and turn it into exam-ready skills. You will find questions covering SDL phases, SDLC mapping, and the differences between popular SDL models. The textbook also covers development methodologies you need to know. Waterfall is the traditional sequential approach where each stage gets signed off before the next one starts. It works when requirements are well understood up front, but it is higher risk because there is no going back. If you miss something in requirements, you are stuck with it until the product ships. Agile is the opposite philosophy. It uses short iterations called time boxes, typically 1 to 4 weeks, and produces working software at the end of each cycle. Scrum is the most common Agile variant, using sprints where a prioritized product backlog drives the work. Requirements evolve through a collaboration, and teams adapt quickly to change instead of fighting it. The SDL presented in this textbook uses a waterfall-style framework for clarity, but the authors make clear it can be adapted to Agile, DevOps, cloud environments, or any combination. Chapter 9 of the book covers how to build your own SDL, tailored to your specific methodology. The exam may ask which methodologies the SDL applies to, and the answer is all of them. Let us talk about the tools that matter in the SDL. There are 3 primary categories: fuzzing tools, static analysis tools, and dynamic analysis tools. Fuzzing is a black box testing technique that feeds invalid, unexpected, or random data into the inputs of a program. You're looking for crashes, memory leaks, and assertion failures. The test design is simple and makes no assumptions about system behavior. Static analysis, also called static application security testing, or SAST, examines code without actually running it. The tool scans source code for common security defects like buffer overflows and unsanitized inputs. Static analysis scales well because it can chew through huge code bases faster than any human could. It also runs at 2 in the morning just as effectively as during business hours, which is something human reviewers cannot claim. But static analysis has limits. It cannot evaluate design flaws or architectural problems. It will not catch poorly designed cryptographic libraries or confusion between authentication and authorization. It also cannot find passwords or magic numbers hard-coded into the source. For those issues, you need human expertise from a seasoned software security architect who understands both development and system architecture at a deep level. Dynamic analysis, also called dynamic application security testing, or DAST, runs the program on a real or virtual processor and looks for security errors while the code is executing. Its big advantage is catching vulnerabilities that static analysis might miss, including false negatives from earlier scans. Think of SAST and DAST as complementary. You want both in your SDL, not one or the other. On the exam, know that SAST and DAST primarily show up during the design and development phase of the SDL, which is the A4 phase in the model we are discussing. The timing matters because running these tools at the wrong point in the life cycle reduces their effectiveness and can waste resources that would be better spent elsewhere. Now let us get into the people side. The textbook is blunt about this. Qualified senior software security architects will make or break your program. These are individuals with 5 to 10 years of development and coding experience who then moved into security. They understand system architecture and software design at the same level they understand security itself. These architects are not the typical security professionals who just run scanning tools. They sit in on every phase of the SDLC. They participate in design reviews, conduct threat modeling, perform penetration testing, and sign off before the project moves forward. Without them, your SDL is a checklist that nobody enforces, and checklists without enforcement produce nothing useful. The textbook also introduces software security champions, or SSCs. These are developers within each product team who have 3 to 5 years of development experience and a genuine interest in security. They are trained by the senior architects and serve as the eyes and ears of the security team inside each business unit. SSCs should be volunteers, not people assigned against their will. As we wrap up this section on tools and talent, remember that understanding these concepts is just the first step. The real mastery comes from applying them, which is where those free practice questions become invaluable. They are completely free and designed specifically to test whether you can distinguish between SAST and DAST, identify the right personnel roles, and match tools to SDL phases. Now we arrive at the security assessment phase, which is phase A1 of the SDL. This is where the project team identifies the product risk profile and figures out which SDL activities are needed. Some models call it the discovery phase. The key output is an initial project outline for security milestones that gets integrated into the overall development schedule. 4 questions drive everything in this phase. How critical is the software to the customer's mission? What security objectives does it need in terms of CIA? What regulations and policies apply? And what threats exist in the environment where the software will operate? If you can answer those 4 questions for a given scenario, you will handle the exam questions about phase A1 without much trouble. The discovery meeting is essentially the SDL kickoff. All key stakeholders sit down and develop a common understanding of the security and privacy implications. They identify sources for security requirements, including laws, regulations, standards, and customer expectations. They flag any certification or accreditation requirements and any third-party or open-source software dependencies. Privacy gets addressed here too, which a lot of older SDL models skipped entirely. The privacy impact assessment process evaluates how the software handles personally identifiable information. The PIA created at this stage is preliminary, designed to guide developers through the early stages. It covers questions like what PI gets collected, how long it is stored, who has access, and what safeguards protect it. The textbook uses Microsoft's privacy impact ratings to categorize risk. P1 means high privacy risk, where the software stores or transfers PII, monitors users, changes settings, or installs other software. P2 is moderate risk, meaning the only privacy behavior is a one-time anonymous data transfer initiated by the user. P3 is low risk, with no privacy affecting behaviors at all. Here is an exam tip about the PIA. The assessment should be treated as a living document. It gets reviewed and updated whenever major decisions occur or the scope changes significantly. Privacy is not something you check once and forget about. It runs through the entire SDLC just like security does, and the exam will test whether you understand that continuous nature. Key deliverables from the security assessment phase include a product risk profile, an SDL project outline map to development milestones, a list of applicable laws and regulations, a threat profile, certification requirements, a list of third-party software dependencies, and a metrics template. Each of these has a specific purpose, and the exam may ask you to match deliverables to their goals. The metrics piece deserves special attention. The textbook makes a point that you should decide what to measure up front and resist the urge to overhaul your metrics frequently. Executives will sometimes ask for different numbers as a project moves along, but constantly changing what you measure defeats the purpose of tracking progress over time. Specific metrics for Phase A1 include how many weeks passed before the security team was brought in, the percentage of stakeholders participating in SDL activities, the percentage of SDL activities mapped to development activities, and the percentage of security objectives that were met. These are the numbers that tell you whether the discovery phase actually produced results. Now let's talk about software security maturity models, because the exam will likely touch on BSIM and OWASP-SAM. BSIM stands for Building Security in Maturity Model. It studies real-world software security initiatives to help organizations figure out where they stand and how to improve. It has 12 practices organized into 4 domains and was built by analyzing data from 9 leading security programs. BSIM measures maturity by looking for evidence of security activities in the SDLC. That is the key phrase for the exam. Not best practices, not procedures, not requirements. Activities. The distinction matters because BSIM is descriptive rather than prescriptive. It tells you what successful organizations are actually doing, not what they should theoretically do. You should also know about CVE and CWE, which are vulnerability tracking resources. CVE stands for Common Vulnerabilities and Exposures and gives standardized identifiers to publicly known security problems. CWE is the Common Weakness Enumeration, which catalogues over 800 types of software weaknesses. The SANS top 25 CWEs prioritize the most dangerous programming errors that make software vulnerable to attack. OWASP-SAM, the Software Assurance Maturity Model, takes a different approach. It is prescriptive and flexible, enabling organizations to self-assess their security program and then use recommended roadmaps aligned to their specific risks. SAM also creates scorecards that let management demonstrate quantitative improvement over time. If the exam asks about a framework that supports self-assessment with risk-aligned roadmaps, SAM is your answer. The ISO IEC 27034 standard also shows up in this material. Published starting in 2011, it provides an internationally recognized way to get transparency into a vendor's software security management process. Microsoft declared its SDL in conformance with this standard shortly after its release. The standard is technology neutral and designed to work across different engineering organizations. On the topic of least privilege, which comes up in Phase A2 but connects directly to what we covered in the security assessment phase, the principle is straightforward. Every user, process, or program should only access the information and resources needed for its legitimate purpose. Nothing more. Privilege escalation attacks happen when someone exploits programming errors to gain access beyond what they were granted. Least privilege applies not just to user rights, but to resource permissions like CPU limits, memory, network access, and file system permissions. During the design phase of the SDL, you determine the minimum set of privileges required for each task and restrict users to exactly that domain. The exam will test whether you can identify least privilege as the correct answer when described as granting only necessary rights and permissions. Don't forget to grab those free practice questions from the link in the description. With the depth of knowledge you have gained today plus practice from those questions, you will be well prepared for your exam. The questions cover everything from CIA and threat modeling to SDL phases, maturity models, and the security assessment deliverables. Let us bring this all together. Software security exists because insecure code is the root cause of most information security problems. The SDL integrates security activities into every phase of the SDLC so that vulnerabilities get caught early when they are cheap to fix. The CIA triad is the foundation of every security decision, and threat modeling done early prevents costly discoveries after release. The security assessment phase kicks off the SDL by identifying risk profiles, establishing milestones, bringing stakeholders together, and initiating the privacy impact assessment. Tools like SAST, DAST, and fuzzing handle the technical scanning. But human expertise from software security architects and champions is what actually makes the program work. Maturity models like BSIMM and OWASP-SAMM help organizations measure their progress. You now have a solid grasp of the foundational concepts in software security and the SDL framework. The exam will test your ability to distinguish between software security and application security, identify the correct SDL phase for specific activities, apply the CIA triad to scenarios, and match tools and roles to their proper place in the lifecycle. Go grab those practice questions, work through them at your own pace, and come back to this video if you need a refresher on any concept. You have put in the work today, and that effort is going to pay off when you sit down for your exam. Good luck, and I will see you in the next video.